Welcome back. We are now doing part 2 of 8.3 notes on bonding theories. In the last part, we talked about several different shapes of molecules, but are there any more shapes possible? And as you can see on the screen, there are definitely other shapes that are possible. If you look at these, you can see only the bonds are being shown here because these are ball and stick models. Unshared pairs are not pictured here, but yet they are affecting those shapes. So in order to understand these different shapes and why these molecules would have those shapes, what we need to understand is something else, which is called a hybrid orbital. Hybridization of atomic orbitals is where two or more orbital types get combined to form a new orbital type that's different from either of the ones that were being combined. Now you might be asking yourself, if I get you to really think about carbon, why is it that carbon can form 4 bonds? Because if we look at its valence electrons, recall its highest energy level is 2s2, 2p2, that suggests that there should be one unshared pair, leaving only 2 electrons available for bonding. So why can't it bond up to 4 times? If we consider this same diagram and recall that a half-full sublevel has extra stability too, what we can do is promote one of these s orbital electrons to that 2pz orbital. When we do that, we get this diagram down here. So this diagram suggests that it can bond 4 times because of the promotion of that electron, and that much is true. But it also suggests that you should have one bond resulting from an s orbital overlapping with another orbital from another atom. And these other bonds should result from p orbitals overlapping with orbitals from other atoms. But experimentally, it's been determined that all of the bonds formed here would be equivalent if we had like methane, carbon bonding to 4 hydrogens. Each of those CH bonds is the same, which shouldn't be if one results from overlap of an s with an s, and the others all result from overlap of a p orbital with an s from hydrogen. What this tells us is that the 4 orbitals are hybridized. We say that 4 of these hybridized orbitals, we'll call them sp3 orbitals, are being formed. So what's going on in hybridization is that several atomic orbitals get mixed to form the same total number of orbitals as there were before. But these new orbitals are all equal in energy. We say they are equivalent hybrid orbitals. For example, if an s orbital mixes with only one of the p orbitals, then we've mixed together 2 orbitals. We get 2 orbitals back out. We would call them sp orbitals because they result from mixing an s with a p. If, however, an s orbital is mixed with 2 p orbitals, then we have mixed together 3 orbitals overall. This is going to result in 3 orbitals being formed. We would call these new hybrid orbitals sp2 orbitals because it results from an s mixing with 2 p orbitals overall to get the 3 sp2 orbitals. If we mix an s orbital with all 3 of the p orbitals, we've mixed together 4 orbitals. So 4 orbitals come out of it, and we call them sp3 orbitals because they come from an s and 3 of your p orbitals being mixed together. Let's look at it in terms of pictures. This shows an s orbital and 3 p orbitals. If you mash them together and come out with 4 new orbitals in the end, we'd have 4 orbitals because we started with 4 orbitals. We would call them sp3 orbitals because they come from having an s with 3 p's mixed together. Now what's going to happen in 3-dimensional space when a carbon atom results in these 4 sp3 orbitals being formed? What we see is we get that tetrahedral geometry that we saw with methane. Because as these point as far from each other in space as possible, those center parts of the orbitals that you see here that look like there's nothing there, that's because that's where the nucleus of carbon would be found. And of course your electrons cannot be found inside of your nucleus. So there's nothing really in that region. So they come down to their smallest point right there at that center part. And that's where they would overlap almost like balloons twisting together. So we get a tetrahedral geometry when you have 4 sp3 orbitals formed. Now that we understand this formation of hybrid orbitals, it's easy to see why methane would turn out to be tetrahedral. Notice we have this carbon on the left, which has all of its s and p orbitals hybridized to form these 4 sp3 hybrid orbitals. When we bring in hydrogens, so that you can have end-to-end overlap between a hydrogen and one of those hybrid orbitals, what results is, over here on the right, as we can see, the methane molecule with 4 sigma bonds. If we look at ammonia and water, we can see that we can understand these shapes from using sp3 hybrid orbitals as well. Looking over here at ammonia, we have these sp3 hybrid orbitals. They're pointing towards the corners of a tetrahedron, but recall that one of them has an unshared pair, not a bonding pair, which is why we get things moving a little bit away from a tetrahedral shape here, but we still have a pyramidal shape. When we look at water, we have 2 of those hybrid orbitals filled with an unshared pair, and 2 of them involved in sigma bonds with hydrogen atoms. So we get a bent molecule of water, and water results from sp3 hybrid orbitals. Now I mentioned that it's also possible to have sp2 orbitals, so let's figure out how they're formed. If you take an s orbital, and you have these 3 p orbitals, but you're only going to mix 2 of them with that s. One of them, the one shown in purple here, is going to remain unchanged. What results is the s with the 2 of the p orbitals mixing together gives us 3 orbitals that we call sp2 orbitals, because it's made from having an s and 2 of the p's mixed together. So we still have 4 orbitals in the end. It's just 3 of them are these hybridized orbitals, and one of them is the unchanged p orbital. Now down here in this bottom picture, we can see in 3-dimensional space how this all works out. Those 3 sp2 orbitals will form in a trigonal planar arrangement. They'll make a triangle all within one plane. And then the p orbital exists above and below that plane. Here's another way of picturing it. You have that yellow plane drawn in there to show you that all of those sp2 orbitals lie within that same plane, and you can see the top lobe of the p orbital extending above it, and you can also see a shadowy form of the other half of the p orbital extending below the plane. So that p orbital is actually perpendicular to all of those sp2 orbitals. And if we look at sp orbitals, those result from mixing the s with only one of the p's. The other 2 of the p orbitals remain unchanged. So in the end, we have 4 orbitals. 2 of them are the unchanged p orbitals, and 2 of them are the sp hybridized orbitals. When we put them together in 3-dimensional space, the 2 sp orbitals end up extending out from each other at a 180-degree angle from each other. So basically, they're lined up in a straight line. Now, that makes it almost look like a single p orbital, but really, it's 2 overlapping sp orbitals, where the only part that really overlaps is that tiny little lobe kind of overlapping a little bit of the big lobe of your other orbital. So we have the sp orbitals, let's say, lining up along the x-axis. Those 2 unchanged p orbitals then can line up along the y-axis and the z-axis respectively. This results in linear geometry because it's the sp hybridized orbitals that are going to be lined up with atoms that they're bonding to. And we're going to see that in just a moment. Orbital overlap with a hybrid orbital will result in a single sigma bond forming. It doesn't matter whether the hybridization is sp, sp2, or sp3. Remember that sigma bonds form from straight-on overlap between orbitals. So our next question, if single bonds are forming from end-to-end overlap of these different types of orbitals, how is it that double and triple bonds get formed? And that's the question we will begin to answer in our final part of these notes, 8.3, Part 3.